Okay, so we're back and today we're going to do the CloudCompare workflow. As mentioned in the previous video, we need to download the .las file from WebODM in my case, the photogrammetry tool. You can get this in other tools as well, but WebODM is open source and you can get the .las file. And the way I like to do things is make sure that all of the project files are in the same place. So for example, in my case, this is the project folder and I already have the QGIS script. I will open a CloudCompare instance. I'm using a Mac, of course, so it might slightly vary in Windows, but it's more or less the same. I will be opening CloudCompare and then make sure to save the file here so that we can track it. And the way I'm going to do that is in the Mac, it's pretty much about typing in CloudCompare. There we go. Let's open it up. And over in CloudCompare, I'm going to drag and drop the las file. Before that, let's also make sure that we have the las file in the inputs. So it has to be here, inputs. Do we have a las file? Yes, we do. What we're going to do is drag and drop it into CloudCompare. And so we'll take this here, and this is the las file, drag it, drop it. You got a couple of default settings which we'll keep, and I'm just going to click on apply all and yes to all as well. It's going to load up the points. Meanwhile, let's just head back here to the main project directory, and here we have this file exactly as how we want it now. And before we do anything else, let's just go ahead and save it. So we're going to go save project and let's select the directory. In my case, it is in the documents folder. I have a folder for QGIS projects. Let's select that and we're going to save it here. I'm going to rename it CloudCompare and the name of the project KCTA. And the file type is a .bin. This works, and as we can see, this shows up here. So now if we were to close this CloudCompare instance, I'm just going to click OK, and we need to open it again. If you double click on this, nothing happens, like you get some weird kind of an error. So what you're going to do is click on CloudCompare, let it open up, and then we're going to go to File, Open Recent, and get the las file, or we're going to go to Open. If you're going to search for a project, head on over to the actual location where you've stored the bin files. That's in this project. Click on it, click open, and we should be on our way. So before we go any further, I also want to show you how to use CloudCompare. This is the actual file. It takes a little bit of getting used to, but you mainly need your mouse and you need to learn how to interact with this 3D model. As you can see, there is this little bit of a sphere around it, and you can use that as a guideline to drag it and move it to different orientations. Now I'm left clicking it to do this kind of an operation. Now if I want to move it around, I'm going to right click it and then I can drag the point cloud around. So what I've done first is I've just aligned it with the QGIS image. As you can see, we have the lake here, that is a pointer. And the lake is outside the scope of the boundary we're working with, but we're going to do all of the further processing to cut to the boundary in QGIS. We're using CloudCompare just to clean up the point cloud and get an accurate digital terrain model. So yeah, this is what we have. We zoom in, just going to move it around a bit. As you move it, you can see that you get a sense for the three-dimensionality of the land. And also you will notice that the underside of the point cloud is actually indicative of the terrain, and that is the actual algorithm we'll be using. It's called a cloth simulation filter, and it simulates a cloth being applied on the underside of the terrain. So it uses that as a base for separating the ground and the non-ground pixels. So we'll do that first, and then we will move ahead with further iterations to clean it up, perhaps setting the filters, setting the different values for the CSF algorithm, the cloth simulation filter algorithm. And if that doesn't work, we're going to do a manual cleanup as well. Okay, so the way we're going to do this is we're going to optimize for classifying the ground pixels rather than the non-ground, because the non-ground we can optimize by doing some manual clipping as well, but the ground is what we need to have sort of the best information possible. That means we don't want the ground pixels to have misclassified any trees as ground, essentially. So what we can do for that is, let's start off with the default values of the cloth simulation filter, and to apply that we need to select the point cloud by selecting that layer, go to plugins, click on the CSF filter, and here you have a couple of options. We're going to select steep slope. What this does is it'll make sure that the ground, which might be sloping, is not misclassified as a non-ground point. And as I said, we're going to lean towards optimizing for ground pixels rather than the non-ground pixels, which we can tweak using some manual classification. So if we select the steep slope option, it will know to not classify the steep slope as non-ground. It is going to be correctly classified as ground. That might be a little confusing, but yeah, as long as you know that we're trying to get as much information from the ground as possible, because it's either this or that, and we're going to optimize for this, which is the ground. Now, selecting steep slope, we're going to click on advanced parameters, and here let's just go with the default values for the cloth resolution and the max iterations. These are the two main parameters we're going to tweak if we need to. I'm going to click OK. It's going to do its thing. Now the cloth resolution is basically, if you imagine a cloth where it's made out of a grid, the cloth resolution, if it's 2, indicates the grid size is 2. And if you go smaller, it's going to become much finer. And if it's a coarse grid, it's going to make it so that the trees or shrubs poke through the cloth filter. And hence, that will be accurately classified as non-ground. But here, the downside is you might lose out on some of the ground pixels being misclassified as non-ground. But as I mentioned, we're going to lean towards extracting as much of correct data from the ground pixels, and everything else can be manually removed, and any misclassified ground pixels, we will need to identify and remove it. With the high resolution of the cloth, what's going to happen is we might have lost some of the ground data because that ground data might have been classified as a shrub. And that is okay by and large, because when we have the flat ground, anyway we're going to interpolate it. All of those trees which are poked out, we don't really know what is the ground below it. So the algorithm will simulate the smooth ground below that, and so we should be good to go. But we also don't want to be removing too much of the ground, because then we lose out on the accuracy of the terrain. Now let's see what we have here. As you can see, after running the cloth simulation filter, we have two levels here, the off ground and the ground points. Now we see we already have a very good idea of the ground, and if we put the trees on top of it, the non-ground points or off ground as it is here, you can see that the off ground points are as such. So we can work with this. Let's zoom in a bit and see what's happening here. This looks like it's a bit of canopy, or which might have been misclassified as a ground point. So let's just go a little more ahead in there. Let's just put the angles. So this is how you actually do this work. You just play around with the 3D model, get a different perspective, and figure out if it is a correct ground point or not. See, this is with the non-ground points. You can see the shadow, which is indicating a canopy. So it's not too bad that we can sort of safely assume that that is the ground. But here there's a lot of lost information. So that's the downside of optimizing for ground points, but it is the ideal way to do things. We can play around with the values till we get something a little more representative of the ground. But for now, I think this is good to go. Let's just zoom out a bit. You can see that the lay of the land is well represented to a large extent. And this is exactly what we need. What I'm going to do is also try to compare it with what we had as an initial automatic DTM classification from the photogrammetry tool, which didn't have any kind of fine tuning involved. What I was suspicious about was this area here. Like, all of this seems like it's properly classified, the slope, but this area seems a bit iffy. And so now again, I've aligned it to the lake being at the bottom, which is here. And this is the part I was a little worried about. As you can see, this has also got the thickest canopy as suspected. And let's just check what the ground points there are. That's the non-ground. Let's just look at this part, give it a little bit of a twirl. Okay, we see that this is the hill. The hill slope is good. Let's just check whether the off-ground has properly got the trees. Yeah, looks pretty good. So I suspect this is a better terrain model than what we had initially without any fine-tuning, because here it suggests that it goes way up and it's a little bit blocky, but here it seems like the slope is a natural slope. And of course, you also need to remember how you walked on top of the land and use that as a reference as well. So it does help to have some notes or some experience through voice notes, or just remembering how the terrain was when you walked around it to get the boundary. This looks pretty good. We might have lost some ground information with this rather large cloth resolution for the CSF, and we've not really played around with too much of the values there. But I'm going to go ahead and complete the process, which is to convert this into a raster and then into a DTM and then import it back into QGIS, and then we can compare it. Okay, so now